Hello, and welcome to a little video about exponential growth. Alright, so let's get started. A famous legend tells the story of the inventor of a game of chess. You should definitely know this game. When the inventor showed this new game to the Emperor of India, the Emperor was so astonished, so impressed, that he said to the inventor, "Name your reward. I will literally give you anything. You're awesome." And the very wise inventor, and we'll find out why he's so wise really soon, he said, "Well, give me 1 grain of rice for the first square, and then give me 2 grains of rice for the second square on my chessboard, and 4 grains of rice for the third, 8 for the fourth, and so on and so on." So let's determine the number of rice grains that he's going to be getting. Well, now let's take a look at this pattern. It goes 1, 2, 4, 8. Hopefully you see that we are multiplying by 2. So let's fill that in. 8 times 2, 16. 16 times 2, 32. Then 64. Then 128. Now we also have a column for powers. So let's talk about the powers of 2. Now in the very first square, we are not doubling at all. So there is no power of 2 happening. That means 2 to the power of 0. Now, for the second square, we do 1 times 2. We multiplied by 2 once. So 2 to the power of 1. To get to 4, we're multiplying by 2 a second time. 2 to the power of 2. Then we multiply by 2 again. That's 2 to the power of 3. Then we multiply by 2 another time. That's 4 2's. 2 to the power of 4. One more time, 2 to the power of 5. And another time, 2 to the power of 6. Forgot this part. Let's write it in. 2 to the power of 6. And then we multiply by 2 yet another time, 2 to the power of 7. Notice how our powers are 1 less than the number of squares. And that's because for our first square, we didn't double yet. So it was 0th power. And what is the pattern? We double. Now, why was this so genius? Well, see how numbers are getting so big so fast? Let's take a look at how that graph looks like. We got the first 3 graphed. For our 4th square, we had 8 grains. For the 5th, 16. For the 6th, 32. For the 7th, 64. And then look, for the 8th, 128. Look at that giant jump. Now the 9th grain of sand, the 9th square would give us so many grains of rice that it's not even on this graph. So that is a giant jump. That's genius. It doesn't seem like he's asking for a lot, but we're going to see in just a moment how many rice grains he gets for the whole chessboard. So let's look at that. I think that's number 7, if it'll load. There we go. Let's find how many grains of rice he has after 64 squares. Now remember, our power was 1 less than the number of square, so we're going to put 2 to the power of 63 into our calculator. Try it. See what you get. I'm going to write it down, and then I'm going to pronounce it for you. You're going to be blown away at how much rice this guy gets. Okay, ready? 9 quintillion, 223 quadrillion, 372 trillion, 36 billion, 854 million, 775,808 grains of rice. He outsmarted the emperor. Oh my goodness. All right. So, based on all of that, let's kind of transition into writing explicit formulas as exponential functions. So, in this explicit formula, and these are from yesterday's sequences, we are going to create the function form. Now, our constant ratio, that is our b term, and our y-intercept is our a term. It's 0, a. And that means our x is 0. When we plug it into our formula, the a refers there, the b is our constant ratio. Okay, so for sequence A, our constant ratio is the same as the explicit formula, it's 3. To find the y-intercept in our calculator, we type in -2 times 3 to the power of 0 minus 1. That gives us -2. Over 3. Whoops, -2 over 3. Oops. Whoopsie doopsie. I was looking at that. I'm like, something's wrong there. -2 over 3. Okay. So, let's write out our function. Our function becomes -2 over 3 times 3 to the power of x. We're going to do the same for the next few. Okay, let's do the same thing for b. For b, our constant ratio is 2. And let's find a by plugging this into our calculators. 45 times 2 to the power of 0 minus 1 gives us 45 over 2. So f of x equals 45 over 2 times 2 to the power of x. And let me color code that. Because I must. I must code the colors. Okay, let's do the same thing for c. We have our constant ratio, 0.1. And we put it into our calculator, replacing our x with 0 because that's how we get our y-intercept. And we get 12,340. So our function becomes 12,340 times 0.1 to the power of x. And let's finish up that last one. Our constant ratio is 1/2. So we put it into our calculators, -5 times 1/2 to the power of 0 minus 1, because the 0 makes it a y-intercept. And we get -10. So our function form is -10 to the power times 1/2 to the power of x. Okay. Now, on the graphs of sequence E and F in yesterday, we could tell that they were not functions. Now, we will practice rewriting explicit formulas in function form and kind of showing that, using that to show that the geometric sequences are not exponential functions. So first, let's turn these into that specific form, that function form. So we need an A, which is us plugging in 0 into x, and then our b is -3. This gives us 4 over 3, ta-ta, ta-ta, and the 0, there we go. So our function would be 4 over 3 times -3 to the power of x. Let's do the same thing for sequence F. Our A is -16 times -1/4 to the power of 0 minus 1. Our B is -1/4. And that gives us positive 64. So our function becomes 64 times -1/4 to the power of x. Now, what makes this not a function? Well, our constant ratio must be greater than 0, but not equal to 1. -3 and -1/4 are less than 0. So they cannot be functions. So, if every arithmetic sequence turns into a linear function, can we say, based on the evidence we just got, that every geometric sequence becomes an exponential function? The answer is no. Not all geosequences have a CR greater than 0 and not equal to 1. That means not all geometric sequences can be exponential functions. Okay, let's fill out the table below. In the geometric sequence is also known as the explicit formula. Gn is the same thing as our f of x, which is our output. G1 over r is actually our y-intercept. It's our a. Our r is the same thing as our b, which is our constant ratio. And lastly, our n is actually our x. That's our input. We just use a different letter. All right. I did a little bit more. Let's do one more interesting problem, and then we'll be done. As a part of a project in health class, Aaliyah, Kim, and Reese are raising awareness and challenging others to eat a healthy breakfast each morning. Today, they sent selfies of themselves eating a healthy breakfast to 4 friends and challenged them to do the same thing the next day. This next day, when others send selfies of themselves eating a healthy breakfast, will be considered day 1. The following day, only those contacted on the previous day will send selfies to 4 friends. The challenge will continue to spread. Let's pretend it's a perfect world where everyone that's contacted participates in this challenge. Now, let's write an exponential function, f of x, to represent the number of new participants. Now, here our y-intercept is going to be the starting point, because that's essentially what it is. So how many people did we start with? We started with 3 people. B is still our constant ratio, our pattern in this case. And that's 4. We send it to 4 people each time. So if our function is f of x equals a to the times b to the power of x, it's 3 times 4 to the power of x. Color code, color code. I must color code. And how did I know my pattern was 4? I forgot to highlight it in our problem, but there it is. 4 friends, 4 friends. Here is the table that's being shown. 12, 48, 192, 768 number of participants. The relationship between the time and number of participants is exponential. Let's verify that by actually seeing or finding the pattern of these new participants. So how do we get from 12 to 48? Let's find out by dividing. 48 divided by 12 is 4. So the pattern is times 4, which is exactly what we said before. So the constant ratio, the CR, is 4. Success. If you have any questions, please make sure to let me know. Otherwise, have a wonderful rest of whatever day it is for you. Bye!